Yeah. No.
And do I have to wait for them to set up? So what that guy teaches? Chemistry?
They had some sort of
These are actually also online too. Okay, so here we go. We have this function. You want everything, don't you? We'll do just. I'll write the answers down now. Yes.
Whenever you're done.
7:15, I'll be done.
Okay. What does that underscore mean?
Yeah, it's supposed to be a complement that was on top of the letters, but I did a copy and paste from that PDF into the Word document. And I thought I did a copy and replace for all, but obviously I didn't. Okay. So just do the best you can, you know, do it according to what's
But it was only 1 point, right? So
Pardon me?
it was only 1 point, right?
1 point.
Your assignment is 1 point towards your entire grade, which might not sound like much.
Well, no, but it says 0 out of 1. It says like 1. It says like.
Right.
Okay.
As long as you did it, you get 1 point. And that's why I did that, so the TAs wouldn't have to spend a lot of time grading. As long as you did it conscientiously, that's 1 point towards your final grade, which is
Thanks.
a lot.
That's a lot of work for 1 point.
So that's 10 points towards your final grade. Pardon me?
It's not graded for like correctness. I did it. I was just asking.
The TAs will look through it and make sure that you did most of it correct. There goes my system. Okay, so wait, how do we have to break this up? Actually, we only need 1 column in the middle. What are the intermediate steps we need here? X plus y? X or y, is that right? We don't even need this, do we? You guys are not engaging here.
No.
We don't need this, do we? 4. 0.
0? 1? You can't see that.
I fixed it so I couldn't do this either. Matt, can you see that okay?
Yeah.
Okay, now we're going to do an AND operation between this column and this column, right? So AND. 0, 0, 0, 1, 0, 1, 0, 1. That's very easy, right? Now what we're going to do is we're going to add on what we did last week. It's got partially wet. I wonder how that happened. So let's create the logic gates for this now. Okay? Any ideas where to start, what gates we're going to use? Okay, let's just review what we have. We have and, or, not, exclusive or, nor, and nan. So far is what we have, right? Okay. So let's go back and do this one first. Since we broke that up into one component, didn't we? So that's an or, correct? And the or is going to look kind of like this. Okay, I'm not going to get an or for that. So there's the input there. And the output is going to go into what? It's going to go into an AND gate, correct? So we have an AND gate here. And the or and the and look almost the same, except for the or has like a concave and the and has a straight. So So this would maybe be X, Y, and Z. Okay, so if I asked you to do that on test, could you do it? Could you do that on test? Yeah. That's a very subtle hint. You know that get that logically program? Did any of you get that logically program? Let's go ahead and do it on the logically program now. I really need for you to be able to do this, so I'm going to put it on the test. I'm probably going to put 4 of these props on the test. Guy. I wonder what his name is.
I'll take that as a maybe.
Okay, so here we're going to start with the OR gate. We have the AND gate. Will be fed by the OR gate. Put a light bulb here.
We don't need to display that on
Good point. Thanks. Busted. It's like so funny to come up here and do this with like three mice, 2 keyboards, 2 screens and that thing. I know I'm making excuses. I appreciate you telling me this. Have you ever like talked to someone, they have this half booger hanging out of them, and you know, do I tell them or just not say anything? Have you ever had that happen?
Depends on how much you like them. You just start doing this.
Right.
Every other word.
Follow me, look at my.
That's funny. You guys are a fun class.
Thank you. Trying.
We'll be here all week.
Okay, so does this match the truth table? Is the thing we got to ask. The truth table that we filled in. Let me see. All right, tell me if we're going to match the truth table by what we do up here. The top one is X, the next one is Y, and the bottom one is Z. So let's see. Are we going to? Is that the right result? X. Here's Y. Here's only Z. Okay, what about X or Y? Still nothing, right? Or what about X or Y and Z?
You should light it up.
Wait, you
That's
don't.
supposed to work.
Oh, it's not all. Okay,
You
yeah.
selected Y.
What now?
Yeah, it's not. Yeah,
You didn't select Y, right?
not sure.
Okay.
Okay.
I thought you said you selected
So that seems to work. So
Y and
what I'm going to ask you to do, has anybody seen next week's assignment?
Yeah.
Did I put logic gates in that? Yes, I did? Yeah. If not, I might go rewrite it. I'll change the rules in the bill. Okay, good. Let's do another one. Next. You don't have to tell me this time. I'm gonna get it before I make a mistake here. All right, here we go. It's really great. Okay. So what do we have to put in the middle here and here? X, Y, X, Z. That's how we need to do? Okay, so X and Y, 0, 0. So far so good? Now we gotta do X and Z.
Is that supposed to be?
0 still again, right? 1. Now we've got to do these two, we've got to forward these two columns now, right? Okay, and so hold that thought. What kind of gates are we going to use to put this circuit together with? 2 and an OR, right? Okay, 2 ands and an OR. So 2 ands. And an OR. And we got to realize that X feeds both of the AND gates, right? So if this is X, it also feeds this over here, correct? Y, and I'm going to put a little bump there so you know it doesn't intersect. So far, so good? We good so far? Vocalizing in a deep voice there. Now let's go ahead and use logically. We can do multiple, so we have 2 ands. Or, so we're going to do the light bulb on this right.
You might have to connect that.
And so this is the X switch, which also feeds this down here, right? And we have the Y switch. And these wires, I found out that they don't intersect if they're just crossing like that. Okay, now. Okay. Did we do that right?
We're going to have these type of problems on the next one, you said, right?
Yes. Obviously, I can't force you to use the software.
Oh, okay, so.
I want you to use the software on your own time, but you're just going to have to draw them.
Okay.
Now, if you draw them on the test and you have the software, then you will be allowed to use the software to check your results. Okay? I'll just make you that concession. If you have your laptop with you during the test, then you can use the software. And the software has a 30-day trial period, so after that test, right, time out pretty quick. Okay, so X, Y. Now we only had 3 results where we got the light to turn on. And obviously, if all 3 of these are on, then it's on. And if X and Y are on, it's also on. So those are the only 2 results we got that turned out positive. Okay, so you just need to know how to do that. And I think I have one more of these to do. Yes, I do. You guys are having so much fun that I thought I'd extend it. Okay, so how are we going to split this up here and here? This isn't the same question I just gave you, is it?
Slightly. Kind of, but you have Z instead of X, Y. You get X, Y.
Okay.
Or X, Z, that's not.
Let's have it not. Which one do you want to not use? Let's not one Y, not the other, okay? Let's not this one. So we need an extra column, don't we? So this would be not Y. This would be X, not Y. And this will be ZY, okay? You with me? Okay, so let's do not Y. 1, 1, 0, 0, 1, 1, 0, 0, okay? So X not Y. I should say X and not Y. So we're going to be looking at these two columns here. X and not Y. 0, 0. We're not going to get any ones, are we? Here we have a 1.
Yeah. 1. 0.
Is that right? Did I get that right? Okay, finally, ZY. Now we're going to look at these two columns. Correct? Okay, so it's an AND operation. Now we have to get our final results. So for our final results, we're going to do this and this will be ORed, right? Now, what kind of gates are we going to use for this? Okay. So, well, I understand why you're saying an AND gate because of this, but it's really going to have to be a NOT. Because if it was an AND, we'd also be involving X. Yeah, so what we're going to do here is we're going to say, we're going to put the AND gate here. We're going to put another AND gate here. We're going to put an OR gate here. But Y is going to feed this as a NOT. Okay. So we have X coming in here. We have Y coming in here, and here, and Z coming in here. Okay. We have this feeding that, this feeding that. We have a result. So let's go ahead and put this on our magic machine. On my super speedy laptop. That's a joke. I hope you know that, right? Okay, so a couple ands, a or, a not. Some switches. Here's the X switch. Here's the Y switch. You put the X on top. You put the Y down. Okay, so it wasn't. I'm sorry. So here's X. Here's one Y input. And I think our truth table had more. Let me see what our truth table had for this. We have 4 true results and 4 false results. So correct. Y by itself. Should be 0. Z. Anyway, you can check all of these. It should turn out to be exactly what the truth table has. Okay, good. So here are some more identities. Which identities did we talk about last Wednesday? The 1x, the 0x, 1 and x, 0 and x, 1 or x, 1 or 0 or y, right? Excuse me, 0 or x, correct? We talked about those. Okay, so what is this? What law can we apply to that? How about commutative? Commutative. How do you say it? I almost said communicative. That would have been a bad word to say on a college campus, right? How about this? Okay, and what's the law?
Commutative.
Commutative. Thank you so much. Okay, is there a commutative that applies to this? or X, right? Okay. Is there a particular law that you can see that we might be able to apply to this? Associative, all right. Oh, I can't abbreviate that one, can I?
Yeah.
I'll try. Laugh at me, will you? Be careful on this one. We're going to use the distributive law here. And this to me is a tricky one. You're just going to have to kind of memorize that one because that's not one of those really easy ones you can figure out. The last one is pretty easy though. So this to me is the one I put a star beside because it's not an easy one in my mind to figure out.
Hold on there, partner.
Sorry. The best way for me to explain it is to make a truth table, and as soon as they're done copying it down, I'll be glad to do that.
Okay. I'll probably that one. As far as the exam, should we attempt to learn the laws by heart, or are we going to have like a reference table, or a reference sheet for the exam?
I don't think I'm going to ask you these, but I will ask you like the 1 and X and the 0 and X. Let's be fair. These will be easy, right? So I'll ask you those. And I'll ask you the more on the test. And I'll tell you what, next Wednesday I'll spend extra time on De Morgan's theorem because I know that there were a few questions. But I'll spend more time with that on Wednesday. I'll have some examples, some illustrations. Okay. All right. That's it for my paper that got all wet. Okay. Okay, so we've kind of been abstracting many functions. Oh, no, don't tell me. Okay. See, what I love about you guys is if I make a mistake, you don't like it. Okay, here we go. So, those are really called combinatorial or combinational, right? So you put these logic circuits together and they do something, right? And they're kind of like on and off. So they don't really have a state except what they are. Okay? So right now we're going to talk about sequential logic, which is really different because there's kind of so these logic gates go from one state to another, and sometimes it depends on where they've come from as far as how they respond. I know that might sound strange, but a lot of times they'll respond one way depending on how they're already set, and another way if they're set another way. So they're not always predictable unless you know what their current state is. Okay. So the first thing we got to do is talk about clock and clock pulses, and pretty much everything in computers has. We haven't talked about clock pulses for those other gates, but now we got to. So what other common devices have this notion of a clock? Come on, IT people. Timers. What about your main CPU? It's got a clock that feeds it and synchronizes everything, right? So what is your clock on at for your PC? 30.4 gigahertz or something like that. It's the same idea, right? So it's a clock that keeps things going. And when your network card is sending stuff out over the wire, have you guys ever thought about how many wires? I know there are 8 wires on your network card. But how many wires really does it take to send the data? Well, really one and then a ground. So there's one data out and then the ground, okay? So how do you get all that data out over one piece of copper? Or fiber or whatever? How does that work? Well, as it turns out, there's a very fast clock on your network card that's going 8 times, or really 10 times faster than the transfer rate. So if your transfer rate is 10 megabits, it's going 100 megabits. If it's 100 megabits, it's going a gigabit. If it's a gigabit, it's going 10 gigabits, okay? So it's always faster than whatever that the data transfer speed is, okay? And what's in your network card that does this is called a UART. Anybody here heard of a UART? Universal Asynchronous Receiver Transmitter? Okay. Oh, damn, this classroom doesn't have a freaking whiteboard. What's up with that? How do you have a classroom without a whiteboard?
It's got a white ball with no board.
Hey, Boo, what are we doing here? Seminars. Don't be early. So you have this really fast clock. And I can't draw all this ups and downs because these are so small. Okay. And then what happens is your network card will send out something that takes up 8 of those. And as long as it's high, or a high voltage, or a plus voltage, it knows that's a 1. And if it goes low, it knows that's a 0, or a low voltage. So what it does is it has 10 of these for each of these, and because it's going so fast, and both sides have the same kind of UART that's set to the same frequency, it knows how to figure that out. But this is the same idea. So your network card is one of the most famous examples of one of these things that's sending out these signals. So other famous things that send out signals, your cell phone is sending them out over the radio, out of the air how often? Very often, right? And what's it doing? It's keeping contact with the cell tower, and it's using something like this. So you notice there are 4 things about this we've got to point out. There's the leading edge, there's the trailing edge, there's the high voltage, and the low voltage. And it used to be that the high voltage was about 5 volts and the low voltage was usually ground. Now the voltages have gone down into the millivolts. And why would that be so important to bring those voltage levels down? Power consumption and heat, right? Those are the things we talked about that are really important to chip design. By the way, does everybody have a pad? You guys got a pad? Yeah, just make sure everybody gets assigned that so that we can justly reward you.
Oh, yeah.
We want to justly reward you faithfully. I should just give you a point. You find a great Jedi.
True. Whatever floats boats.
Okay. So here's a rising edge, the falling edge, the high voltage, the low voltage. It's actually not very accurate to use the high and low voltages just because where is the high voltage? Well, it's a wide area like that. So, Alex, you're just in time to get the extra credit sign up.
What?
Extra. I'm rewarding the faithful few. And he drives a motorcycle, so you got to give the guy a break with the ring, right?
It's pretty bad outside.
Yeah. So everybody who's here gets a credit because, as you can see. So, but we give you kudos because you came on a motorcycle. So normally the high voltage and low voltage are going to be fairly constant. So it's a little bit tough to find the exact, precise, discrete high and low values. Normally they use the rising and falling edges. I went to agree that picture with. So circuits that change states on the rising edge or falling edge are called edge-triggered. Level-triggered circuits are change states when the clock voltage reaches highest or lowest. The problem with that is where's the high? It's a pretty consistent value, so that's a tough one, and so is the low. Okay, so this idea of feedback in this example is pretty lame, but it's an important idea for when we get to the next couple of examples. So what if Q, the output, feeds back into the circuit? Can the circuit ever possibly change? All right. So what if there's what if it's a 1? What's going to feed through if it's a 1? When it gets through, it'll be a 1, right? What if it's a 0? When it feeds through, it'll be a 0, right? So already we've adopted this idea of state, right? Like I said, this is a pretty lame example. I got it. But it easily illustrates the point of where we're headed. Okay, now this, what are these two gates?
4 gates.
They're or with a, there's a little circle.
NOR gates.
NOR gates, right? They're NOR gates. Okay, so what's with this? What would we call this? According to what we just talked about, this would be more feedback, right? So we're not holding the whole circuit one way, but we're feeding back into one of the inputs. Okay. And what's really interesting about this is that depending on, so let's say you feed S, and it is going to do a flip-flop. It's kind of like politicians, you know what I'm saying? And it'll actually change its state. Okay, so there's the truth table. When both inputs are 0, there's no change when the clock resets, when the clock triggers. When R is 1, it resets to 0. And when S is 1, it sets it to 1. And 1 is undefined. But there's a variation on this shortly that we're going to talk about that does define. Okay? So notice, this doesn't give you necessarily a state. It says reset and set, right? So it's just a change of state, correct? So here we go. There's S and R, and there's Q. Okay, and so Q indicates that feedback, right? And it is significantly affecting the output state that you get. And notice we have 2 at the very end that are undefined, and we're going to talk about another kind of flip-flop that actually takes care of that issue and is able to use them. Okay. So this is called a JK flip-flop, which then has a slightly different truth table. That doesn't have those undefined states anymore. Okay. And the reason is just because internally how it's able to hold the state of those so they're not undefined. You notice how there are 2 AND gates in front of it now? And they're both getting fed back? Okay. And this is a D flip-flop. And the only thing you have to notice here is the same as the first flip-flop we looked at, except for that the 1 gate has a NOT, okay? And actually, how much data feeds it? 1 bit, right? So every time that bit changes, the state of a flip-flop changes. Okay. Questions? Comments? All right, so in honor of your faithfulness, I think it's 7:15, is it not? Don't you guys have 7:15? I don't wear a watch, but I thought it was 7:15. So. Okay. Anyway.